In this video, we're going to use the intermediate value theorem and apply it to an interest problem. And so the first thing I'm going to do is just state the theorem, which the wording seems confusing, but the actual theorem itself is very simple to use. The theorem states that if f of x is continuous on a closed interval, ab, f of a not equal to f of b, and L is any number between f of a and f of b, then there exists at least one number c between a and b such that f of c equals L. It's an awful lot of words, a lot of symbols. What it's basically saying is that for a continuous function on this interval a and b, so if you choose basically some value, if there's some value c between a and b, that f of c will fall between f of a and f of b. And the best way to show this is just to draw a picture. So I'm going to start by just drawing 2 points. So I'll mark off an a, which is just some x value, and b is my second x value. And I'll just draw a point, one point that has an x coordinate of a, and some other point that has an x coordinate of b. And I'm going to just connect them with a smooth curve. So I want, basically the function needs to be continuous on AB, so we've drawn a continuous function. And if this function is f of x, then the y coordinate of the point right here, this point A, is going to be f of a. So this will be my f of a. And then the y coordinate that goes along with the x coordinate b will be f of b. And basically what the theorem states is as long as this function is continuous, that there exists some c between a and b. So I'll just choose some c that falls between a and b. And if I mark off, I go up to the graph, I know that the y value corresponding to that x value is going to be f of c, and that f of c is guaranteed to fall between f of a and f of b. So I've got a continuous function on AB. There exists some f of c such that c is between a and b. And this is an existence theorem, so it doesn't necessarily tell us what that c value is. It just tells us that it exists. So let's look at an example. We have a function here. We want to use the intermediate value theorem to show that the polynomial f of x equals x cubed plus 2x minus 1 has a 0 or x-intercept on the interval from 0 to 1. So I start off by just confirming that the intermediate value theorem applies here, and it does because this function right here is a polynomial, and polynomials are continuous everywhere. So if it's continuous everywhere, it's going to be continuous on the given interval. And my job is to show that there's an x-intercept somewhere between x equals 0 and x equals 1. Basically meaning that the graph crosses the x-axis between 0 and 1. So basically what I want to do is I want to show that f of x equals 0 for some x between 0 and 1. So the first thing I'm going to do is I want to find f of 0. So when I plug 0 into the original function up here, I get negative 1. And I also want to find out what f of 1 is. And when I plug f of 1 in the original function, I get 1 squared, which is 1, plus 2 times 1, so that's 2, plus 1 is 3. 3 minus 1 is 2. So I know that f of 0 is equal to negative 1, and f of 1 equals 2. And so because I have a sign change from -1 to 2, in order for my y values to go from -1 to 2, it means there has to be some y value in between there that is equal to 0. I had to have hit 0 as long as this is a continuous function. And so without graphing the function f of x equals x cubed plus 2x minus 1, just to kind of demonstrate that point, if you have here f of 0 is -1, and then f of 1 is equal to 2. If this is a continuous function, no matter what the shape is, whether it is a straight line or a curve, it could curve more than once, but every single one of the functions that I drew had to have crossed the x-axis. So we're saying, okay, well, if the y value was negative down here, negative at my first point, I'm at -1, and up, so my smallest value is -1, and my largest value on the, or not necessarily the largest value, but on f of 1, the value is 2, that somewhere, since I went from -1 to 2, my y value has to equal 0, and it happens. Doesn't tell us where it happens, we just know it happens between x equals 0 and 1. So I'm going to graph the function y equals x cubed, so x raised to the 3rd power plus 2x minus 1, and I'm going to do a zoom 6 just to give me a standard 10 by 10 window, since I know what I'm looking for has to happen between 0 and 1. And it's hard to, with the window that I have here, it's actually a little bit harder to see. So what I'm going to do is I'm going to make my x, my window and my x a lot smaller. I'm going to go from -2 just up to 3. The values that I'm interested in are really just between 0 and 1. So I'm just going to go a little bit beyond 0 and a little bit beyond 1. And I'm going to graph this again. So we can see here that the graph does cross the x-axis between when x equals 0 and when x equals 1. And even though, again, the theorem tells us that this value exists, it doesn't tell us what the actual value is.